Hello students, welcome to the EN 401 lecture on Archimedes principle and hydrostatics. So here's the roadmap for this lecture. We're going to start with talking about vessel terminology, then we will discuss static equilibrium and buoyancy, then on to Archimedes principle, and finally hydrostatic pressure. Alright, so some basic vessel terminology. Hopefully everyone is already familiar with this, but we have a cross section of a ship here. So what that means is we have a ship and we sliced it down the middle at amidships, and now we're looking at the inside of the ship from the side. So here's all our vessel terminology that we'll need to solve problems for this lecture. So some standard terms: the width of a ship is called the beam, or B. The height of a ship from the keel is the depth. The bottom of the ship is the keel, or K. Right, so we should all know that ships are usually built up from the keel, so the very bottom of the ship is the keel. Draft is the distance from the keel to the water line. And freeboard is the distance from the water line to the top of the ship. So freeboard plus draft equals to depth. There's also a video link here at the bottom, so go ahead and pause here and watch that video link if you would like more information on vessel terminology. All right, so some more vessel terminology. We want to talk about the center of gravity of our vessel. So any vessel has some type of mass, and that mass is acted on by gravity. So therefore a ship, any kind of vessel or ship, has a center of gravity, and we need to be able to define where that center of gravity is. So we have three measurements, or three essentially coordinates that we use to find center of gravity. We have the vertical coordinate, which we call the kg. We have the transverse coordinate, which is the port or starboard measurement, so we call that the tcg. Right, so you'll see that if your center of gravity is located to the port, then you'll have a negative tcg. If your center of gravity is located toward the starboard, you would have a positive tcg. And then we have the longitudinal center of gravity, and that's measured along the ship's length. So we could, start at midships is 0, and moving towards the bow is positive, and moving towards the stern is negative. All right, so why do ships float? It's a big question, right? So if a ship or an object is not accelerating, then it's said to be in static equilibrium, right? So we'll just think about a ship that's just sitting in very still water and floating. So if it's just floating there, that means it's in static equilibrium, and therefore some of the forces on the ship are equal to 0, right? Because it's not accelerating up or down, or left or right, or forward or backwards. And some of moments are also equal to 0, so the ship isn't experiencing rotational acceleration. It's not just kind of spinning there. It's sitting there floating nicely, right? So static equilibrium. Right, so we're going to need to analyze what forces are occurring on the ship so we can figure out how it's in static equilibrium. So we know the ship has a weight, and that weight acts at the center of gravity. Right, so we'll call that weight delta S, and that delta S acts at the center of gravity. And so if we've got a force going down, then we need obviously a force going up, and that force going up is the buoyant force, FB. And the FB is exerted by the fluid at the center of buoyancy, right? So this bottom bullet here, gravity and buoyancy are of equal magnitude in opposite direction and act at their respective centers. So let's take a look at what static equilibrium looks like for a floating vessel. Right, so we know that the vessel or ship has a weight called delta S. Right, and delta S is going to be located at the center of gravity. Right, if we just looked at this one force, if there's only this one force acting on this system, then we wouldn't be in static equilibrium. The ship would be moving down, accelerating down, it'd be sinking. But we're not sinking, we're floating. So there must be some other forces at play here. And so those other forces, or that other force, is the buoyant force. right? And the buoyant force acts at the center of buoyancy, right? So this could possibly be in static equilibrium. So let's look at our equations. We can say that some forces in the y direction are equal to 0. So we have delta S going down and FB going up. So delta S must be equal to FB for this to be in static equilibrium. We also need to check our moment equation, right? Sum of moments about an arbitrary point. So we could just say this arbitrary point is where that red X is, right? That's equal to 0. So for there to be no moment, right, the distance for both delta S and FB from our reference point must be 0 or the same number, right? If you chose a reference point over here, right, those are still the same perpendicular distance away, so you'd still have no net moments if you chose that reference point. So yes, so for the ship to be in static equilibrium, delta S and FB must be coplanar. They must be located on the same plane. All right, and the center of buoyancy is located at the centroid of the submerged area. Right, so the centroid of the submerged area is going to be the location of your center of buoyancy, right? So if we took the centroid of this shape here that I'm outlining in red, the centroid of that shape would be where our center of buoyancy is located. All right, so we have a ship here, and the ship is leaning over. All right, so is this ship in static equilibrium, and why or why not? So if we were to look at this ship here, we would say that this ship is not in static equilibrium because the center of buoyancy and center of gravity are not on the same plane, right? There is a perpendicular distance between those 2 points, right? And that means there is a net moment on this ship. So if there's a net moment, we're not in static equilibrium. So what's going to happen is the center of buoyancy is going to try to rotate the ship back this way. So how can we get in this situation? Well, one way we could get in this situation is, let's say there was a wind that was blowing, and now the wind stops blowing, right? But the ship is listed over because of that wind, and now our ship is in this fashion, and the buoyant force is going to push it back up. You could also have waves that cause the ship to do that, or if the ship is moving and it turns and it does that, we'll see a similar thing, but that's kind of in the realms of dynamics, so we're just looking at statics here. All right, so we got the same ship, but now we see that the center of gravity has moved over, so it is coplanar with the center of buoyancy. Is this ship going to be in static equilibrium? Why or why not? Well, the answer is yes, it will be, because the center of gravity and center of buoyancy are coplanar. They're in line with each other, so some forces in the y direction would equal to 0, and some moments about an arbitrary point, let's just say this point, right, that would be equal to 0, because the perpendicular distance between the center of gravity and the center of buoyancy and that arbitrary point is 0. So this ship is in static equilibrium, and what would cause this situation? Well, what causes this situation is you maybe put a lot of gear on this side of the ship, which caused the center of gravity to shift off the center line, and because the center of gravity shifted off the center line, the center of buoyancy also had to shift to off the center line to keep the ship in static equilibrium. So we'll have a lecture coming up on how to calculate how the center of gravity moves, but for Archimedes principle in this lecture, just know that the center of gravity and center of buoyancy have to be lined up. So if the center of gravity is not on the center line, then neither will the center of buoyancy. All right, so we know that delta S and FB are the two forces acting on a ship in static equilibrium, but we need to really figure out how to determine delta S and FB. So we've got four methods. The first method is, hey, we could take our vessel and we can stick it on a scale, right? That's an easy one. The only problem is it's not the most practical for a lot of the large ships we have in the Navy, right? We're not exactly going to be able to take an aircraft carrier and put it on a scale and get its weight. So might be good for small ships or small boats, but not going to be great for anything that the Navy is really deploying around the world. The second method, we can use the displaced water volume method, right? So we can see how much water is displaced by a ship, and we can collect that water and weigh that water. And we'll see some correlations on how we do that in next few slides. We can do the submerged volume method and the hydrostatic pressure method, right? So we'll move on and we'll go through all of those methods. So some helpful terminology before we get to that. So this symbol here is called rho, right? Rho is density, and density is mass per volume. So some typical units of density are kilograms per cubic meter or slugs per cubic foot. And this other one here, that is gamma. So gamma is unit weight, and unit weight is equal to density times the gravitational constant, and that gives you weight per volume. So typical units are newtons per cubic meter or pounds per cubic foot. You'll probably see pounds per cubic foot most in EN 401. So typical values of gamma are going to be 62.4 pounds per cubic foot for freshwater, or 64 pounds per cubic foot for salt water. And salt water is obviously has more weight per unit volume because it has lots of salt. So that increases the unit weight and the density of salt water. All right, so take a minute, pause the video here, and go ahead and watch this video on Archimedes' principle. This is sort of the beginnings of how to determine forces acting on objects in water or fluid. All right, so I hope you learned something from that great TED video on Archimedes' principle. But we'll go through what he said basically in words. So Archimedes suggested that any object wholly or partially immersed in a stationary fluid is buoyed up by a force equal to the weight of the fluid displaced by the object, right? So basically, the buoyant force is equal to the weight of the object, which is equal to the weight of the water displaced by the object, right? So if an object weighs 1 pound and you put it in water, it's going to displace 1 pound of water. Right, so that's sort of that second point here. Any floating object displaces its own weight of fluid. Right, so the submerged volume of the object is equal to the volume of the water displaced. Right, so if you have an object that has 1 cubic foot of vessel below the water, that means it's displacing 1 cubic foot of water. Right, so another point here is an object that is sinking, in the process of sinking, or has sunk to the bottom, and it's 100% submerged. It is displacing its entire volume of water, where something that is floating is only partially submerged and displacing only the amount of only the volume of water of what's below the water line. So let's take a look at some examples of Archimedes' principle, right? So kind of see how this is all working. So we have this tub of water here. So the tub is this black set of lines down here in the bottom, and it's full of water to the brim. So that blue line at the top represents water, and then we have 2 objects that we have placed into the tub once we fill it up. We got object A, which is floating, and object B, which is in the process of sinking. All right, so we got some questions. So which of these 2 objects is in static equilibrium? Well, A is floating, right? So we already know that if it's floating and it's not moving, then it's in static equilibrium. But object B is sinking, which means it's moving, right? It's moving in that direction, and therefore our object B is not in static equilibrium. All right, so the second question is object A displacing its weight or volume of water, and why? Remember, Archimedes said that for an object that is floating, it will displace its weight of water. So object A is displacing its weight of water. Right. Then the next question is object B displacing its weight or volume of water, and why? Well, object B is sinking, right? So object B is fully submerged, and therefore it is displacing its volume of water, right? Object B is under the water, so whatever volume that object B is taking up, it is pushing that volume of water away, right? So object B is displacing its weight of water. All right, so the next question, if both objects have the same weight, which one displaces more water? So this is sort of a tricky question. So let's just say object B is very, very dense and object A is not very dense. Then we can say that object A is displacing more water because the volume of object A that is below the water line, right, is going to be larger than the volume of object B below the water line. To get volume, essentially the way you can think about it is to get volume, or to get object B to float, you need to add volume. And once once object B's volume equals to at least the submerged volume of object A, then object B would float, right? Because they're the same weight. So if you got volume B to have the same exact volume as the submerged volume of A, object B would start floating. If you decrease the volume of B so that it sinks, right, then that's when it's going to start to go down. So object A is displacing more water because there's more volume under the water. All right, so next question, assuming the tub was full prior to A and B being placed in, did any of the water spill out of the tub, and why? Well, yes, right? We know that when we place something in water, it displaces water, right? So if it's floating, it displaces its weight of water, right? If it sank, it's displacing its volume of water, right? So we put object A and object B in, and that water is going to spill out of the tub, right? So what do we call that water? We call that the displaced volume, right? So the water that's going to come out of the tub is the displaced volume. And what correlations can be made from this water? Well, for object A, we know that the water that's displaced when object A is placed in, if we collected that water, the weight of the water displaced when A was placed in would equal to the weight of A. For object B, if we placed object B in the water, it would displace its volume. So if you collected the water and you weighed the water and made some correlations, you could figure out the volume of B. All right, so Archimedes' principle and static equilibrium. So we know that the buoyant force and delta S, the weight of the object, are equal to each other, and we need to make a correlation between those two. We know that the volume displaced can be correlated to the weight of the object, and the way we make that correlation is through the unit weight of water. So we can say the buoyant force is equal to the specific weight or unit weight of water times the volume. All right, and if we do a unit check here, so our gamma is going to be in pounds per feet cubed, and our volume would be in feet cubed, right? So these would cancel, and we'd be left with pounds as units, and we know that pounds is a force, so our equation checks out. So how do we calculate the volume displaced? Well, if we have a nice rectangular prism object, we can just say the length times the width times the height of the object that is submerged, or the length times the beam times the draft. Remember, T here is draft. All right, so that's how much of the ship is underwater. So the length times the beams times the draft gives you the volume displaced. And we know generic values for gamma H2O, so we can figure out the weight of the ship and also the buoyant force acting on the ship, right? Because the buoyant force is what's holding it up, and the weight is what's trying to drag it down, and those have to be equal and opposite for our ship to be in static equilibrium. All right, so here's an Archimedes application question. So go ahead and pause the video here and try to solve this one. And make sure you use this big hint here. Find the displaced volume. So calculate displaced volume for each of these, and then you can figure out which one is going to displace more water. So go ahead and pause now and do that. All right, welcome back. So hopefully everybody figured out that there's no real difference between A and B. They're both floating, and they're both 62.4 pounds. So both A and B are displacing 1 cubic foot of water, right? So CF here means cubic foot. So both A and B are displacing 1 cubic foot of water. All right, so we've got our sunken lead weight here, and its unit weight is 624 pounds per cubic foot. So you should have figured out that our sunken lead weight is displacing 0.1 cubic feet of water. So that means our sunken lead weight is only 0.1 cubic feet of volume, and so it's only displacing 0.1 cubic feet of water, and so C is displacing the least amount of water, and A and B are both displacing the most at 1 cubic foot. So the next method we're going to use to calculate the delta S or FB is the hydrostatic pressure method. Well, what is hydrostatic pressure? That's pressure exerted by a fluid due to the force of gravity, i.e. it's the pressure exerted by the weight of fluid above an object. So what does that look like? Well, we got a cross-section of some water here. So if we're at the, on the surface, we're floating on top of the water, right there, there's no water above us, so we're not feeling any hydrostatic pressure. But as we go deeper below the surface, right, we see that hydrostatic pressure, which is modeled by these arrows here, we see that hydrostatic pressure increases, right, and increases in a linear fashion, right? So the deeper we go below the surface, the more hydrostatic pressure, and the pressure is related to the density of that fluid and how deep below the surface you are. So let's take a look at those equations. Right, so pressure is going to equal density times gravity times the height above wherever we are referencing. So if you wanted to find hydrostatic pressure at this point X over here, you would just need the height, this height of water here. Right, so we know that density, or rho times G, equals gamma. So to make the equation a little simpler, we can say that pressure equals gamma times the height of water. So pressure doesn't help us too much getting delta S. We need another equation. So we need to figure out how to turn pressure into force. Well, pressure is just equal to, force is just equal to pressure times area. So we've got the pressure calculated, we just need an area now. Well, let's say we are using a rectangular flat bottom vessel, and it's got these dimensions. So this view here, that's if you're underneath the ship looking up at the keel, and this view here is a cross section of the ship. So we have this rectangular ship with almost a square cross section. Right, so we need an area. So the area we're going to use is the area of the keel, right? So the area of the keel is just beam times length, right? So if we're looking up at the bottom of the ship, our area of the bottom of the ship is beam times length. All right, so we know that pressure is gamma times H, and in the case of our ship, H is the draft, right? So T is equal to H for our pressure equation. T is draft. All right, so now we can turn that into a force equation. Right, so buoyant force is going to equal to our pressure, which is gamma times T, times our area, which is the beam times the length. So if we look at this ship and all the hydrostatic forces that are acting on it, if we were kind of going to graph those, we'd see that on the sides of the ship, you have no hydrostatic pressure right here at the water line, and it increases in a linear fashion until you get to the keel. And then once you're at the keel, there is a constant value of pressure because you are at a constant depth across the keel. So the water pressure on the keel for a flat bottom ship is equal at any point on the keel. And then we can see the buoyant force is located at the centroid of our submerged area here. So that's our center of buoyancy. And then our center of gravity is located elsewhere, and that is based on weight and dimensions and loading of our ship. All right, so here's an example that you can use all of the knowledge you've learned in the Archimedes principle to our lecture to solve. So go ahead and do that. There is an extra video for you to watch to get the solution. Here's another example. Go ahead and give this a shot and then watch the example problem video. All right, so here's our review. So make sure you know the difference between KG, TCG, or LCG and TCG. Understand the four methods to find the displacement of a ship, which will equal to the buoyant force, unless, of course, your vessel is sinking. So if our ship is floating, that is true. All right, understand how static equilibrium comes into play in floating ships, and understand how to use hydrostatic pressure to calculate a force, right? And understand how that force is acting on a ship and how that correlates to FB, right? That correlates to FB. All right, that's it. Hope you enjoyed. Thanks. Bye-bye.